partial fraction video. So the first step here in the partial fraction expansion to write this complicated thing as a sum of simple things is to factorize the bottom. So I recommend factorizing using the AC method, so that's what I'm going to do. So we have 2s squared plus 11s plus 12. So I multiply the a by the c, that's the 2 by the 12 there, and I get 24. And I look at all the factors of 24. So I get 1 by 24, 2 by 12, 3 by 8, 4 by 6, 5 doesn't go, and 6 I already have. And what I want to be able to do is make up that plus 24 using a pair of these which add up to 11. And plus 3 and plus 8 do the job. So I now rewrite this as 2s squared, and I rewrite the 11s as 3s plus 8s. I still have this plus 12. Okay, so that's the crucial step in the AC method, and then it should be okay from here. So take something common out of the first two terms, s. What am I left with? 2s by s gives me 2s squared, plus 3 by s gives me 3s. And then take something out of the 8s plus 12, that leaves 2s plus 3 again, and that would be 4. Okay, and now what you have is you take out the common factor of 2s plus 3. And note, we're not solving this equal to 0, we're just factorizing it. Although that's going to be useful in a minute. So take out the common factor 2s plus 3, and you're left with s plus 4. Now, this is going to be 2 rule 1s because these are distinct linear factors. They're different. Okay. So let me just look at where we go on the next page. Okay, I'm going to have loads of space here. That's okay. So take the original f of s, which is 7, but write it not over the 2s squared plus 11s plus 12, but the 2s plus 3 times s plus 4. Now the rule 1, you've got two factors, says you're going to have something over 2s plus 3 plus something over s plus 4. And this something are constants, a and b, which we have to find. Okay, so now what I do is I say, okay, I want to find the a and b such that these are equal for all values of s. So what is recommended, and there are slightly different methods, but what I'm recommending is you write the thing on the right as a single fraction. Now to add fractions together, you need a common denominator. So to get a common denominator, I recommend you use 2s plus 3 times s plus 4. So let's see how that goes. So I want this to be 2s plus 3 times s plus 4, and I can get that by multiplying above and below by s plus 4. The crucial thing is that this blue thing here, the s plus 4 divided by s plus 4, is equal to 1, and multiplying by 1 doesn't change anything. Now it looks different, but it's the same number. Multiplying by 1, like 7 by 1, looks different to 7, but it's the same number. And similarly, b over s plus 4, I'm going to multiply above and below by 2s plus 3. Now, of course, the order of multiplication doesn't matter because these are all just numbers. So the important thing is that these things are just equal to 1. They don't change anything. So now we have a common denominator, which is, say, 2s plus 3 times s plus 4. And look what we have on top. A times s plus 4 plus b times 2s plus 3. Now, we want the 7 over 2s plus 3 times s plus 4 to equal the a over 2s plus 3 plus b over s plus 4. And we've shown that that a and b thing is equal to the thing on the bottom. So now what we're saying is we want these two things to be equal. So I want them to be equal. The exclamation mark is kind of like a sense of urgency. The bottoms are the same. So no issue with the bottoms. They're equal. So if I want these things to be equal, what I need is I need the tops to be equal. I need the 7 to equal this. Okay. Now in terms of the notation in the previous section, if we just look at it, just to wrap everything up. So the U of S is the top of this thing. So in terms of the notation of what we were looking at, the 7 is the U of S. And then this is the V of S. And what we want to do is set these two things equal to each other. So that's what we've done on the bottom of this page. Set the top of the left equal to the top of the right, if you can do it so that they have the same bottoms. So now you've got two options, okay? So the one that I'm recommending is that you take the U and the V and you just sub in different values of S. Say SI, SI. Usually you'll be able to do this in a clever way, and you'll see the clever way as we go. So this is kind of, yeah. Now then there's a method, this is kind of more like chapter 2, where you kind of, the coefficients must be the same. So you're comparing, this is like before. So remember, you'd compare how many t's there were on the left, how many on the right, what was the constant on the left, what was the constant on the right. I'm usually always going to include method A, but you might kind of end up doing method B from chapter 2, and that's absolutely fine as well. Okay, so anyway, what we have to do on the next page is set these two things equal to each other, and we're going to do method A, which means we're going to plug in values of S into both sides of this, and there's clever ways to do that. And what we want to do is we want to find A and B. Okay, so let's look at what we got. So we want to say that 7 is equal to, that's the top of the thing that we started with, and the top of the partial fraction expansion written as a single fraction, then compared to top. So this is what we want. So the clever values to pick, now I've given the clever values there, but we'll start with, we'll make it a bit easier. So kind of clever values are 0, S equal to 0. So these two basically are supposed to be equal for all values of S. So whatever value of S you get in, you input, you get out a relationship between A and B. And if you put in two values of S into both sides, you'll have two equations in A and B, you can find them. But you can be a bit cleverer. So kind of clever values typically would be 0, S equal to 0 makes things easy, S equal to 1. But there's clever methods again. If you want, you can pick a clever value of S that makes that equal to 0. So if you have a thing like, what is the value of S that makes that equal to 0? It's -4. So we're going to substitute in S equal to -4 into both sides of this. What do we get? We get 7 is equal to A times S equal to -4 plus 4 gives me 0. Plus B times 2 times -4 plus 3. And what's A times 0? Well, that's just 0. So you get 7 is equal to A times 0, 0. I won't include that. And the other yoke is like -8 plus 3 is B times -5. Now you're interested in finding A and B here. So divide both sides by -5. You get that B is equal to -7/5. Okay, now the other thing then is you want to be able to kill two. So I made a comment about finding the roots. So maybe it is actually useful to find the roots. So for example, finding the roots of 2S plus 3. In other words, find that equal to 0. That's the other value of S you want to put in. That'll help you find A. So if I run with that, I get 2S. So take away 3 from both sides and then divide both sides by 2. So that's where this -3/2 is coming from. So I now put in S equal to -3/2 into both sides, and I get 7 is equal to A. Now, yeah, A, I'm looking for A. -3/2 plus 4 plus B, and the point was we chose a value of S that made 2S plus 3 equal to 0, so this is equal to 0. So we end up with 4 minus 3 over 2, which I think is 5 over 2. So it's 7 is equal to 5 over 2 times a. Now we'll go a bit quickly. I think a lot of us here might multiply by 2 and divide by 5. But look, ultimately a is just multiplied by 5 over 2. So if you divide both sides by 5 over 2, you can be done a lot quicker. So 7 divided by 5 over 2. I probably shouldn't use a calculator for that, for it's going to be 14 over 5. And therefore you find that's the original thing we had, the complicated thing, which was even more complicated because it wasn't factorized. 12 is equal to big A, which is 14/5 over, I'll have to go back and check which one is A related to. A is over the 2s plus 3. Plus B, which is minus 7/5 over s plus 4. Now what we'll be hoping to do eventually is to send the thing on the left back into the time domain. And the first thing you do is do this partial fraction expansion where you write it as two simple things, which is in there. Now one of the things I have to say here is that the 2s plus 3 is not quite in the table. So we'll do a little bit of algebra here. So one of the things you see in the tables is that e to the minus at is sent to, by the Laplace transform, 1 over s plus a. Well, you've got 2s plus 3. Now what you really want to do here is with the 2s plus 3, there's different things you can do. If you don't want the 2s, you want an s, you could divide the bottom by 2. Now dividing by 2 is the same as multiplying by a half. And so what you can do is you can multiply above and below by a half. I appreciate some of this is a little bit complicated here. So what I want to do is, I don't want 2s plus 3, I want s plus something. So if I multiply the bottom by a half, that's the same as dividing by 2, the 2s will turn into an s. But I have to multiply the top by a half as well. So if I do that, so the half by the 14/5 is 7/5. Okay. And then the half by the 2s plus 3. So half by 2s is s, half by 3 is 3 over 2, minus 7/5 s plus 4. Now I need to send this back, but so sending it back, of course, is going like in that direction. And what you might notice is the kind of, we've 1 over what's going on with these 7/5. So maybe let me say that, think about this number here. Say this number here to yourself. That orange number, what is that? If you say 3 over 4, that doesn't really mean anything. What I'd like is for you to say, that's 3/4. So similar story, 7/5 divided by this is 7/5 times 1 over s plus 3 over 2 minus 7/5 times 1 over s plus 4. And now we can send this back using the inverse Laplace transform. So this goes back to the time domain, fix the 7/5. What does 1 over s plus a go back to? E to the minus at. So this goes back to e to the minus 3 over 2t. Fix the minus 7/5 because the Laplace transform is linear. That means you can go term by term fixing constants. So the inverse is as well. And then the 1 over s plus 4 goes back to e to the minus 4t. Now you should know from chapter 2 that when you've got two negative exponentials, this one goes to 0 faster. So this goes to 0 fast. This one goes to 0 slow. I'm just going to write slow. And so you have an overdamped, this is actually corresponds to an overdamped oscillator. The graph looks like that. If you put t equal to 0 into that green thing, you'll get out 0. And basically what this probably corresponds to is an overdamped oscillator with a good initial velocity. But look, once it reaches that maximum amplitude, it takes ages to get to 0, relatively speaking. So it's overdamped. If you if you were to make the damping a bit weaker, there's a few things that would actually happen. So I better not mess around with that graph. Okay, so that's to explain these things. So let's go and look at another example. So we'll be doing a lot of examples here, but you will have to back it up by doing your own examples. Right, first of all, factorize the denominator, the bottom. So I have s squared plus 6s plus 9. So the AC method, the A is 1, the C is 9, so that's 9 and it's plus 9. Now one of the good things here is a lot of the factorizations, and I'll explain why. So usually we'll be interested in negative exponentials, because if you have a positive exponential, something that's getting bigger and bigger and bigger. Now if it's a function of time, you don't have systems with positive exponentials. Things don't get bigger and bigger and bigger because they'll break. So usually we'll be talking about negative exponentials, and if they're negative exponentials, that means that you got like s plus a, s plus b. When you're factorizing, there's not going to be many negatives around. Now that's not a promise, but yeah. So anyway, let's factorize. So it's plus 9 is what I'm saying. It's easy. So I get 1 by 9, 2 doesn't go, 3 by 3, 4 doesn't go, 5 doesn't go, 6 doesn't go, 7 doesn't go, 8 doesn't go, 9. We already have 9, so we're done. Can we make a plus 6 using a pair of these? We can do plus 3 and plus 3. So let's rewrite this thing here as s squared and rewrite the 6s as plus 3s plus 3s plus 9. So we'll take out a common factor out of the first two here, s times s plus 3, and take something out of the second two, the 3s plus 9, that leaves s plus 3 again. The answer would be 3. Now remember, you can pause this. And now I've got a common factor of s plus 3. So I take out that common factor of s plus 3. Okay, now I'm just going to look ahead there what I'm looking at. Right. So now here you notice that you have repeated factors. So this is a rule 2 because it's repeated. You've got s plus 3 twice. Okay, so off we go back to the original thing. We have 8s plus 15 divided by s plus 3 squared. Okay, I'm going to look at another method for this one afterwards. Not yet though. So the rule 2 says you're going to have something over s plus 3 plus something over s plus 3. But what are you missing out on here? Well, it's so if you do say a and a b, you might, if you try and do it with that'd be a good exercise. Can I find constants a and b that make those two things equal to it? You won't be able to. So you need to, according to rule 2, change the second one. Okay. So what does the method say then? The method then says that you should write the thing on the right, the partial fraction expansion, as a single fraction again. So we need a common denominator. So what you should use is s plus 3 squared. So what you should do, how do you get s plus 3 squared with the a over s plus 3? Well, you need to multiply it above and below by s plus 3. Okay. So now it doesn't look like it, but we have a common denominator. Now I'll do an extra line here just in case you can't see it. So you have a times s plus 3, and then the s plus 3 by the s plus 3 is s plus 3 squared. And then you have b over s plus 3 squared. And so you have a common denominator. You have a times s plus 3 plus b all over s plus 3 squared. Okay, now you want the thing on the left to equal the thing on the right. The thing at the a and the b turns out to be equal to this thing at the end. So you want these to be equal. So let's say you want these to be equal. If you look at them, the bottoms are the same. So if you want them to be equal, what you need is for the tops to be the same. Okay, so we're going to do that on the next page. The 8s plus 15 equal to that. So what was it? A times 2s plus 3. No, not 2s plus 3. S plus 3 plus b. Okay, so this is what we want. So, so what you can do is compare. Like if you look at it, if you could write out the thing on the right and get as plus 3a plus b, and then if you compare coefficients like chapter 2, the a would have to be 8. So that would be an option. Okay. I'm not going to do it that way. I'm going to recommend that you substitute in values of s. So the cleverest value to throw in at the moment is to throw in s equal to minus 3, because that will kill the s plus 3. So substitute in s equal to minus 3 into both sides. So you get 8 times minus 3 plus 15 equal to a times 0, killing the a, plus b. And so you get the b kind of quite easily. B is equal to 15, looks like minus 24, is it? Minus 9. All right, yeah. Okay. Now, you can't kill anything else. But so now just the cleverest value is just to put in a random value. You can put in whatever you want, but the cleverest thing to put in is s equal to 0. So you put in s equal to 0, you'll get a times 0, that's handy, plus 15 equal to a times 0 plus 3 plus b, but the point is you know b is minus 9. So tidying up everything, you get 15 is equal to 3a minus 9. If you add the 9 to both sides, you get 3a is equal to 15 plus 9, which is 24. And then divide both sides by 3, you get a is equal to 8. Okay, so what we've shown is the complicated thing we had at the start. Was it 8s plus 15 over s squared plus 6s plus 9, which is not in the tables, is in fact equal to a, which is 8, over s plus 3 minus 9. Is it? Ooh, I don't like this. No, I do like it. Okay. Now, what I'm going to show here is how you'd send this back using the tables. But before I do, I must kind of look at the shortcut. So there is a shortcut to some of this. Now, it doesn't always work. I think I'll have to do it up the top of the page. There's not much room, but I'll just about do it. So the shortcut works. It needs more skill, but it can be done. I may as well show it to you. So you have 8s plus 15 over s plus 3 squared. And the idea is to get, is this going to be easier? The idea is to get an s plus 3 on top. Okay, so you do something like this. Yeah, it's not actually that easy at all. Maybe it'll scare you away from it, and that's okay. So if you get 8 times s plus 3, now that does the 8s plus 24. But there should be a 15. So to get from 24 to 15, you need to do minus 9. And now you can split this up as 8 times s plus 3 over s plus 3 squared minus 9 over s plus 3 squared. And then you can divide above and below by s plus 3 in the first one to get 8 over s plus 3 minus 9 over s plus 3 squared. Easier, perhaps not, but it is an option. Okay. Now what I want to do is want to send this thing back. So some of the things that we've seen is, and you'll see from the tables, and I will send you on the tables, 1 over s plus a goes back to e to the minus at. So that first term is going to be no problem. The second one is harder. So the second one, first of all, it's shifted because instead of s, it's s plus 3. So the shifting theorem says, okay, as normal, you send f of s back to f of t. That's just the normal notation. But the first shift theorem says that if the s is shifted to s plus a, when you send it back, you must multiply by this negative exponential. Now we will be covering all of this again. Like at the moment, this is all that you're supposed to get to, but we're just kind of looking ahead. There's no harm looking ahead. So just, it'll be explained multiple times because it is difficult. So what I'm saying here is that this the second term, the 9 over the s plus 3 squared, it's actually like a 9 over s squared, but shifted. Now, can we deal with a 1 over s squared? Well, we can, because we have in the tables that 1 over s to the n goes back to t to the n minus 1 over n minus 1 factorial. All these arrows are inverse Laplace transforms. Okay, so I'm going to rewrite this thing slightly differently. So I'm going to rewrite it as 8 times 1 over s plus 3. And I'm going to do similar here for the 9 times 1 over, now I'm going to do s squared, but shifted, the s is shifted to s plus 3. Now let's send it back using the inverse Laplace transform. Okay, so we can fix the 8, the 1 over s plus 3 using the top thing in the tables here. That's e to the minus 3t. We can fix the minus 9. Now what does the first shift theorem says? So we need to make a comment here. So this here is a shifted 1 over s squared. So the first shift theorem says that if it's so you're looking on the left here, the big F s plus a. So if it's a big F s plus a, you just bring it back as normal, as if it's not shifted, and then multiply by the exponential shift. So you must bring back 1 over s squared as normal. So the 1 over s squared comes back using the bottom of these three formulas. So it'll go to t to the power of n minus 1, that's 2 minus 1, all divided by 2 minus 1 factorial. But because it was shifted, we must multiply it by e to the minus 3t. So we'll tidy this up a little bit now. So this is equal to 8 e to the minus 3t. Now the 2 minus 1 is 1. 1 factorial is 1. So it's just minus 9 divided by 1. T to the power of 2 minus 1 is just t to the power of 1. It's just t. And then you have this negative exponential. And look at the fact that the two exponentials have the same speed. And what that means is that you've got critical damping in context. Now, you probably can't say it's critical damping without seeing the original differential equation. You see, the thing so what we're dealing with here, the 8s plus 15, I'll show you where that actually arises. That would arise here. So we're saying we've had the differential equation, we've taken the Laplace transform, we've solved the resulting algebraic equation, and now what we're doing is, well, the thing we're focusing on is writing it as a sum of simple terms. That's the partial fraction expansion. But once you've done that, realistically, what you're looking to do is send it back. And that's what we're doing here, sending it back. Okay, so I think that'll be absolutely loads for your first week of Laplace. I will be probably trying to do 2 hours a week so that we finish it nice and early, and you can have loads of invest a lot of time into doing exercises.